When designing a modern seawater reverse osmosis facility, engineers do not simply pump seawater through a membrane rack. They must overcome the natural osmotic pressure of high salinity water, typically around 25 to 30 bar for standard open ocean seawater, and significantly higher in enclosed basins like the Arabian Gulf or the Red Sea. Pushing pure water molecules across a polyamide thin film composite membrane against this osmotic gradient requires massive high-pressure pumping energy. In this episode, we examine how modern plants optimize specific energy consumption, deploy isobaric energy recovery devices, manage membrane flux and scaling, and tackle the complex engineering trade-offs of brine management and zero liquid discharge. Let us open the process flow diagram. Every successful SWRO installation begins long before the high-pressure pumps, at the intake and pre-treatment train. Raw seawater is notoriously aggressive. It contains suspended solids, organic matter, marine algae, and bacteria that pose an immediate threat to the downstream spiral-wound reverse osmosis elements. Engineering practice in 2026 relies heavily on robust multi-barrier intake strategies. While open ocean intakes are common, subsurface intakes, such as beach wells or seabed galleries, are increasingly preferred where hydrogeologically feasible because natural sediment filtration drastically reduces silt density index, or SDI, and biological loading. Once the water enters the plant, the pre-treatment train must prepare it for the high-pressure stage. Standard pretreatment typically incorporates coagulation, flocculation, and dual media granular filtration, or increasingly polymeric ultrafiltration and microfiltration skids. Maintaining an SDI below 3 and a turbidity under 0.1 NTU is non-negotiable for preserving membrane permeability. Furthermore, precise chemical conditioning, including acid dosing for pH adjustment and specialized antiscalants, is continuously injected to prevent calcium carbonate, calcium sulfate, and silica precipitation on the membrane surface. Skipping or compromising pretreatment is the single fastest way to induce irreversible biological fouling and catastrophic flux decline. With pre-treated feed water conditioned and pressurized, the heart of the plant takes over, the high-pressure pumping and membrane rack assembly. High-pressure pumps, typically high-efficiency multi-stage centrifugal pumps driven by variable frequency drives, boost the feed water pressure to anywhere from 55 to 80 bar, depending on feed water salinity and operating temperature. Inside the membrane racks, feed water enters fiberglass-reinforced plastic pressure vessels housing spiral-wound polyamide composite elements arranged in multi-stage arrays. As water flows tangentially across the feed channel of the membrane, pure water permeates through the polyamide active layer into the permeate carrier, while the remaining brine increases in salinity as it travels toward the reject port. Hydraulic design here requires careful management of recovery ratios per pressure vessel and array stage. If the recovery rate is pushed too high in the first stage, the concentration of sparingly soluble salts, such as barium sulfate, strontium sulfate, and silica, exceeds their solubility limits near the tail end elements, causing severe mineral scaling. Engineers must balance permeate flux rates, typically maintaining conservative flux rates between 12 and 15 liters per square meter per hour, or LMH, to ensure stable long-term salt rejection and prevent accelerated membrane conversion. Energy has historically been the primary operational cost driver.
This SWRO sprayed pack refreshes, don't appear weight.
Through the optimized integration of isobaric energy recovery devices, or ERD, and high-efficiency pumping trains, state-of-the-art seawater reverse osmosis plants operating in 2026 have pushed specific energy consumption, or SEC, down to less than 2.5 kilowatt-hours per cubic meter of permeate produced. Yet, engineers must remember that this figure is context-dependent. High salinity feed water, colder water temperatures increasing fluid viscosity, and smaller plant capacities will naturally elevate SEC beyond this baseline. To maximize freshwater output and reduce intake and pretreatment sizing, modern design increasingly turns toward high-recovery seawater reverse osmosis, or HRSWRO. Traditional single-stage SWRO plants typically operate at recovery rates between 40 and 45%, meaning more than half of the intake seawater is returned to the sea as concentrated brine.
Pushing recovery to 60, 70, or higher requires sophisticated multi-stage configurations. In a typical two-stage high recovery setup, the reject brine from the first SWRO pass, which still possesses considerable hydraulic energy, is routed through an intermediate booster pump or specialized high-rejection brackish water membranes. Alternatively, intermediate chemical conditioning or partial hardness removal is applied between stages to mitigate mineral scaling of calcium and sulfate ions. While high recovery configurations dramatically increase water production efficiency and reduce unit footprint, they introduce severe operational challenges. Operating at higher recovery rates concentrates scaling precursors exponentially and increases osmotic pressure in the second pass, requiring higher applied pressures and robust anti-fouling membrane chemistries. Engineers must weigh the capital expenditure of additional membrane skids and interstage boosting against the operational savings of reduced intake water volume. Every drop of permeate produced leaves behind an equivalent volume of concentrated brine, enriched with anti-scalants, cleaning chemicals, and elevated salinity. Managing this reject stream is one of the most critical environmental and engineering challenges of our time. For coastal facilities, traditional brine disposal relies on engineered outfalls with multi-port diffusers designed for rapid initial dilution within permitted mixing zones. However, in enclosed water bodies, inland desalination plants, or strict environmental jurisdictions, ocean disposal is restricted or prohibited. This has elevated the importance of minimal liquid discharge, or MLD, and zero liquid discharge, or ZLD, technologies. ZLD systems aim to recover nearly all water from the brine stream, leaving only solid crystalline salts. A typical ZLD train combines brine concentrators, mechanical vapor compression evaporators, and thermal crystallizers. However, engineers must maintain a realistic perspective. ZLD and advanced MLD are exceptionally capital-intensive and energy-demanding. They are not universal solutions for every plant. Consequently, current engineering research heavily emphasizes brine valorization, extracting valuable minerals such as magnesium, lithium, and sodium chloride from the brine before final disposal to partially offset operational expenses. Even the most advanced SWRO design will fail prematurely without rigorous operational control and real-time diagnostic monitoring. Plant operators must continuously track several critical control variables: normalized permeate flow, normalized salt passage, differential pressure across each membrane stage, and feed water temperature compensated conductivity.
Modern plants integrate machine learning models into their SCADA systems to forecast membrane fouling rates and optimize anti-scalant dosing dynamically, transitioning maintenance strategies from reactive breakdown responses to predictive, condition-based interventions. As we conclude our examination of desalination engineering in 2026, let us synthesize this into a practical site decision framework for engineers and project managers. When evaluating a new desalination project, your design choices must follow a rigorous hierarchy. First, conduct comprehensive feed water characterization across seasonal extremes, analyzing not just baseline salinity, but organic carbon, temperature fluctuations, and boron concentrations. Second, select your intake and pre-treatment technologies based on raw water variability, prioritizing ultrafiltration and robust coagulation where biological loading is high. Third, optimize your high-pressure architecture by pairing variable frequency high-pressure pumps with isobaric energy recovery devices to drive specific energy consumption toward baseline efficiency limits. Fourth, evaluate whether high recovery configurations or brine minimization, including MLD or ZLD, are genuinely required by local environmental regulations or whether well-designed outfalls suffice. Desalination engineering is a masterclass in balancing thermodynamics, economics, and environmental stewardship. By grounding your designs in verified engineering data and site-specific constraints rather than generalized promises, you ensure long-term plant reliability and economic viability. Thank you for watching Water Atlas. In our next episode, we step away from the coast to explore advanced wastewater treatment, membrane bioreactors, aerobic granular sludge, and biological nutrient removal. Make sure to subscribe, consult the references below, and keep engineering with precision. Engineering practice in 2026 relies heavily on robust multi-barrier intake strategies, including subsurface beach wells and seabed galleries that drastically reduce silt density index and biological loading. Once the water enters the plant, the pre-treatment train incorporates dual media filtration, polymeric ultrafiltration, and precise chemical conditioning, including pH adjustment and anti-scalants to prevent mineral scaling. With pre-treated feed water conditioned and pressurized, the heart of the plant takes over, the high-pressure pumping and membrane rack assembly, boosting pressures from 55 to 80 bar. Inside the membrane racks, feed water enters fiberglass-reinforced pressure vessels housing spiral-wound polyamide composite elements arranged in multi-stage arrays. As water flows tangentially across the membrane, pure water permeates through the active layer, while brine increases in salinity as it travels toward the reject port. Energy has historically been the primary operational cost driver in seawater desalination. Without energy recovery, passing seawater through reverse osmosis at 70 bar would consume prohibitive electrical power. Fortunately, modern desalination engineering has been revolutionized by advanced energy recovery devices, specifically isobaric pressure exchangers that transfer up to 95% of hydraulic pressure directly without mechanical conversion. Through optimized integration of isobaric ERDs, state-of-the-art SWRO plants operating in 2026 have pushed specific energy consumption down to less than 2.5 kilowatt-hours per cubic meter. To maximize freshwater output, modern design increasingly turns toward high-recovery seawater reverse osmosis, pushing recovery rates from traditional 40 to 45% levels to 60, 70, or higher via multi-stage configurations. Every drop of permeate produced leaves behind an equivalent volume of concentrated brine. Managing this reject stream is one of the most critical environmental and engineering challenges of our time. While coastal facilities utilize engineered outfalls, inland facilities turn to minimal liquid discharge and zero liquid discharge technologies, combining brine concentrators, mechanical vapor compression, and thermal crystallizers. Even the most advanced SWRO design will fail prematurely without rigorous operational control, tracking normalized permeate flow, salt passage, and differential pressure across membrane stages for early failure diagnostics. As we conclude our examination of desalination engineering in 2026, evaluate feed water quality, optimize energy recovery constraints, and balance brine management constraints to ensure sustainable plant performance. Thank you for watching Water Atlas. Stay tuned for Episode 3 on advanced wastewater treatment and nutrient removal. Keep engineering with precision.